So today we're going to be talking about E2, which is a type of elimination reaction. And basically in elimination reactions, we always go from a single bond, a sigma bond between a carbon and a carbon. This carbon always has to have a hydrogen, and this carbon has to have a good leaving group. And always you're going to go from this to an alkene. That is what an elimination does. Two types of elimination reactions are E1 and E2. For now, we're going to be talking about E2. So what does an E2 reaction need? First thing it needs is a good leaving group. So good leaving group. Okay? What are some good leaving groups? These are your halides, so your chlorines, your bromines, your iodines, and also your sulfonates, so your sulfur compounds. These are called sulfonates. I'm just going to write that down. You can look them up. A good example that we've talked about in lecture is OTS. So keep that in mind. So I'm going to put this in parentheses, OTS. Okay? And another thing we need is a strong base. What's an example of a strong base? The common example that we're going to be talking about today is NaOH. Very common, and you're going to see this reagent very frequently. Another one, which is going to be a bulky base, which you have to keep in mind, is DBU. Okay? DBU does something funky that we'll delve into later. Okay? So, talking about an E2 reaction, basically, we also need an anti-periplanar arrangement of the hydrogen and the leaving group. So what does that mean? That means if we were to look at the Newman projection down the bond, the hydrogen, let's say if the hydrogen were here, right, and you have your R groups here and here, behind it, in the carbon behind it, we need a leaving group over here, okay? Exactly 180 degrees to this hydrogen, and then other R groups here. Okay? So this anti-periplanar arrangement is necessary in order for this elimination reaction to occur, because when your strong base comes in to take your hydrogen, that is how the bond forms. It needs to be on the opposite side of the leaving group so that the leaving group doesn't get in the way. If the leaving group gets in the way, then this reaction isn't going to occur. It has to get into a conformation where the leaving group is on the opposite side of the hydrogen. Okay? So let's start talking about an example. So one example of an E2 reaction would be this. So over here we have Br. Br is our good leaving group, and to this we're going to add NaOH. So take a second and try to think about what sort of products are going to form. Okay? For this reaction, I'm going to write up my products in blue for this specific reaction, and then I'm going to do another reaction with a bulkier base and see what sort of happens there. Okay? So product of this reaction would be majority. So you have two products for this reaction, right? Because we have hydrogens here and here. Okay? I'll label these hydrogens, hydrogen, hydrogen, and there's one hydrogen there, right? We also have one hydrogen there, but I'm going to write this in green because I don't want you to ever deal with this hydrogen right here. Think as if this hydrogen doesn't exist, because you never ever pull that hydrogen away. Okay? Regardless of its properties, NaOH is going to pull this hydrogen or one of these hydrogens, and now we see which one would be dominant. Okay? So dominantly, we're going to pull off this hydrogen. Why this hydrogen? Because this is in a more substituted position. We have 1, 2, 3 R groups on this carbon, making this carbon more substituted. Therefore, that hydrogen will be pulled more frequently. So here, OH's negative charge is going to pull this hydrogen. This hydrogen is going to form that bond, and then this Br is going to leave. That is your mechanism for an E2 reaction, right? Just these three things happening all in one step, okay? That's why E2 is a concerted reaction. Concerted meaning happens all at once. So the product of this reaction would look like this. Double bond there, R group 1, R group 2 there, and that's that. This is your Zaitsev product. So label this Zaitsev. and that is going to be your major product. Now you do also get the other product when you take this. Here, I'll do this in a different color so you guys can see this better. Let's use pink. So NaOH coming in and attacking one of these hydrogens. This hydrogen is going to leave, form that bond. Br is still going to leave like normal. So that's that E2 reaction. This is going to form your Hoffman product. Hoffman. Just like that. And what this will look like would be that. So this is your minor product because a less substituted alkene is less stable than a more substituted alkene. That is why this is a major product, okay? Now this happens because we have such a small base, okay? This turns out to be your major product, that's your minor product. Now what if we use a bulky base? Now if we use a bulky base, something a little bit different happens. So I'm gonna do this in pink, because why not? If we do use DBU, which is a bulky base, DBU is gonna grab one of these hydrogens much more frequently, doing basically the same exact thing as NaOH did for the minor product. And the product of this is going to form a major Hoffman product. So DBU would favor Hoffman, and it'll have a minor product of Zaitsev. Okay, and these are the two products formed. The products don't change, it's just these are the two products formed. This is now major and that is now minor if we use DBU, okay? So that is what happens if we use a bulkier base. Now, in this case, we really didn't have to worry about an anti-periplanar arrangement because these bonds rotated and there's two R groups that are the same here, so we didn't have to worry about it being cis or trans. So let's use an example where we do have to worry about that. Let's work with a ring. For example, how about a 6-membered ring that has a tert-butyl group here, wedge, and let's have a leaving group over here that's going to be behind us. So Br right there, okay? Now let's say we add NaOH to this, simple enough, common base. What's going to happen? So we have to think about the chair conformation, right? So what will this look like in its chair conformation? Let's draw our template for a chair. Something like that. And let's place our tert-butyl group. So our tert-butyl group would favorably be equatorial. Energetically favorable, it should be equatorial. If it is not equatorial, then this reaction will only proceed with high energy. So let's see if that works out. So if we place this equatorially, let's say right over here. So tert-butyl group is going to be right there. Now let's start counting carbons away until we hit our leaving group, right? So we have 1, 2 carbons away, and then we're going to have our leaving group, which is going to be pointed down. So 1, 2, and our leaving group is going to be pointed down. So Br is going to be down here, like so. Okay? So will this work out? Will this go through an E2 reaction? Yes, it will, because Br is axial, and this is a much more stable conformation. If we did a chair flip, however, this Br will become equatorial, and this tert-butyl group will become axial, and therefore the reaction for E2 will not occur. Okay? So what will the product of this look like? Well, we have some options again. We can pull off hydrogens from here. Oh, that's supposed to be axial. So more like this. Hydrogen there, or a hydrogen there. Or we can pull off a hydrogen from here, or like that, okay? It's important to note that the hydrogens that will be pulled off are the axial hydrogens, okay? So the only ones that we can actually pull off are either going to be this one or this one. So keep that in mind. So it doesn't matter which one you pull, but note that you will pull both, so you will have a mixture of products. So OH minus is going to come in and take that hydrogen, for example, that's going to form that bond. Br is going to leave, and you'll form this product, which will look like this. Double bond straight down there, just like that. Okay? Now, instead, if OH came in and pulled off the other hydrogen, the other axial hydrogen, that gets pulled off, this forms that bond, and Br still leaves. So that product will look something like this. Like that. Okay, so these are the two products formed. Neither is more favorable than the other because neither is more substituted than the other, right? That is where this whole Zaitsev and Hoffman comes from. If one product is more substituted than the other, that's going to be the favorable product. But in this case, this has one R group and that has one R group. So, and this also has one R group and that has one R group. So they're equally as stable as each other. So that is the whole anti-periplanar arrangement. If we were to basically do the Newman projection looking down this bond, we would see that the hydrogen would be pointed straight up and the Br is pointed straight down behind it. That is the anti-periplanar arrangement that I'm talking about, right? So that's basically that for E2. So keep in mind, E2, you need an anti-periplanar arrangement, you need a good leaving group, and a strong base, okay? He gave you a few examples of some strong bases, and I'll go over that again in a different video. Thank you.